So today I am explaining this bond parameters. First bond parameter we are taking here bond length. So this bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. That is equilibrium distance between the nuclei of two bonded atoms in a molecule is called bond length. So first I will write a definition. The equilibrium distance between the nuclei of two bonded atoms in a molecule is called bond length. This bond length is measured by spectroscopic techniques, X-ray diffraction techniques, and electron diffraction techniques. By using these techniques, we can measure bond length. It is measured by spectroscopic X-ray diffraction and electron diffraction techniques. And it is expressed in, this bond length is expressed in, it is measured in angstrom units and picometer units. So it is measured in angstroms and picometers. Okay. Now bond length, for example, bond length between a set of same atoms in different molecules is the same. Bond length between a set of same atoms in different molecules is the same when the hybridization is the same. For example, so I am writing first statement here. The bond length between a set of same atoms in different molecules is the same if the hybridization is same. For example, bond length between oxygen and hydrogen is the same in water H2O, in hydrogen peroxide H2O2, and in alcohols methyl alcohol or ethyl alcohol. So in all these compounds, bond length between the oxygen and hydrogen is the same, that is 0.97 angstroms, because in all these compounds hybridization is the same, that is sp3 hybridization. If hybridization is different, then bond length between that oxygen and hydrogen is different. When the hybridization is same, the bond length between the two atoms, that is oxygen and hydrogen, any two atoms bond length is the same in different molecules when the hybridization is the same. That is condition, hybridization is same. If hybridization is changed, then bond length between the two atoms also changes. For example, so for this one I am writing here example. H2O, H2O2, hydrogen peroxide, and ethyl alcohol, you take C2H5OH. So in these three compounds, bond length, the oxygen hydrogen bond length is 0.97 angstroms. In these three compounds, the oxygen hydrogen bond length is 0.97 angstroms. Because in these three compounds, hybridization is the same. That is, the hybridization is H2O, in H2O2, in ethyl alcohol. In these three compounds, hybridization is the same, that is sp3. That's why in these three compounds, oxygen hydrogen bond length is the same, that is 0.97 angstrom. So this value they are given experimentally. So this is first one. So H2O, water. So this is the water, and H2O2. And ethyl alcohol, C2H5OH. So in these three compounds, oxygen hydrogen bond length is the same. That is, just now we have written, that is 0.97 angstroms. And next one, as the p character in hybrid orbital changes, bond length also changes. In hybrid orbitals, p character, percentage of p changes, then bond length also changes. So I am writing statement, as the p character in hybrid orbital changes, bond length also changes. So how it changes? I am writing here, p character is directly proportional to bond length. P character is directly proportional to bond length. See example, C to H2. So this clear structure I am writing acetylene, that is CH triple bond CH. Next ethylene, CH2 double bond CH2. Next ethane, CH3 single bond CH3. So here hybridization is sp because triple bond. Here sp2 double bond. Here single bonds sp3 hybridizations. Now in sp hybridization, p character is 50%. I am writing here p character, and here p character is 66.7%, and here p character is 75%. 75%. Now bond lengths are here. Bond length 1.06 angstroms, 1.08 angstroms, 1.09 angstroms. So you observe here p character increasing, then bond length also increasing. So p character is directly proportional to bond length. So bond length is depending on p character in hybrid orbitals. So this is second one. As the p character in hybrid orbital changes, bond length also changes. How it changes? That is, both are directly proportional. P character is directly proportional to bond length. Example, acetylene, ethane we are taken. So here sp hybridization, here sp2, sp3, and here in sp, p character is 50%, here p character 66.7%, p character is 75%. Therefore, bond lengths 1.06 angstroms, 1.08 angstroms, 1.09 angstroms. Next, as the number of bonds between two atoms increases, bond length decreases. As the number of bonds between two atoms increases, bond length decreases. Because as the number of bonds between two atoms increases, bond strength increases. So therefore bond length will be decreases. As the as the number of bonds between two atoms increases, bond length decreases, because as the number of bonds between two atoms increases, bond strength increases, therefore bond length will be decreases. Example, carbon to carbon, if single bond is there, then bond length is 1.54 angstroms. Double bond is there, 1.34 angstroms. If triple bond is there, 1.20 angstroms. So between two atoms, one bond, two bonds, three bonds. Number of bonds increasing, bond length decreasing. Bond length decreasing. Next, as the size of the bonded atom increases, bond length also increases. As the size of the bonded atoms increases, bond length increases. Because size increases, therefore bond length increases. For example, HF, HCl, HBr, HI. So here H is common in these compounds, and fluorine, chlorine, bromine, iodine. So halogens, from fluorine to iodine size will be increases. So here iodine has large size, so HI has large bond length, more bond length. So here from HF to HCl bond length increases, from HCl to HBr increases, HBr to HI also increases. This is bond length increasing order, because size of the atoms increases here, that's why bond length also increases. Next, this bond length is affected by resonance. Bond length is affected by the resonance. For example, see benzene. I am taking here benzene. So 3 double bonds in benzene alternatively. When this double bond shifted to here, and this is shifted to here, and this is shifted to here, we get another structure like this. Double bond, double bond, double bond. When this bond is shifted to here, and this is shifted to here, and this shifted to here, then we get this structure. So these two structures are interconvertible. These are called resonance structures. So you observe here single bond is there between here one is carbon, here also carbon. The junctions represents carbons. So between these two carbons, a single bond is there. But in this structure, in these two carbons, double bond. Between these two carbons, here double bond, here single bond. Single bond, double bond. Single bond is not constant here, double bond is not constant here. Single bond changes into double bond changes into single bond. If carbon to carbon single bond is there, what is the bond length? Just now we are written 1.54 angstroms like ethane. And if carbon to carbon double bond is there, 1.34 angstroms. Just now we are written CC double bond. But here single bond is not constant, double bond is not constant. That's why in benzene bond length in benzene, that is 1.39 angstroms. 1.39 angstroms. Between these two bond lengths, here in benzene, carbon-carbon bond length is there. In benzene, bond length between all the carbons is the same. Between these two carbons, between these two carbons, between these two carbons, bond length is the same, that is 1.39 angstroms. So that's why we are written here bond length is affected by the resonance. So actually if carbon-carbon double bond is there, bond length should be 1.54. If double bond is there, 1.34. But in resonance, due to resonance, single bond is not constant and double bond is not constant. That's why bond length is in between these two. We are written here 1.39 angstroms.